Hi guys. I'm gonna set up actually. I'm gonna set up a computer really quick. Well, welcome everyone. Hi, my name is Sarah. I'm a recruiting specialist here at GoPro. I've been here for about a year and a half, and so I actually help support all of our U.S. departments along with Europe. So I'm just here to talk to you very quickly about our recruiting program. So I could probably talk for hours about how amazing all of our teams are across the world, but I'll keep it short for about 2 minutes. We thrive in an extremely collaborative environment. We actually have some of our employees throughout the room, so feel free to meet them afterwards. But I'll go through quickly. This year has been absolutely amazing. I don't know who's kind of kept in touch with what we've been doing, but over the last few years, we recently just launched about 2 weeks ago 3 new products, well, new-ish, our Fusion, which is a 360 camera, our Hero 6, and then we've added additions to our GoPro app. And so with that being said, we couldn't have done any of that without our amazing teams. So most of the people in this room right now are in engineering. And so these are actually current positions that we have up right now for our teams in San Mateo. So with that being said, if you guys have, any friends, family, we have tons of positions open across the board. So marketing, IT, other engineering positions across hardware, also in our San Diego office. So feel free to check out our GoPro page. Tons of positions open for you guys to take a look at. If you are interested in any, I highly suggest applying directly online and just mentioning that you came to this event so we know exactly how you found out about us. Unfortunately, I cannot stay too long today, but I will give my information to Chester and he can share it with all of you afterwards, so feel free to connect. Thank you. Also, anyone that sits in the front gets a T-shirt or hat, so just saying.
Thank you. So I'm Bob Carlson. I'm Director of Product Management for our software platforms here, and one of the positions up there belongs to me, and I'm looking for someone who can really kind of come in and bring a lot of big data experience and kind of help guide the nature of our platform and how we can really add value to the company. We've got a really interesting situation here where we're talking software, behavioral data, hardware data, sales, finance, marketing. All of it is kind of coming together under Chester's platform, and we really want to kind of help guide that roadmap. So if you have any interested people who might be able to contribute, please send them our way. We've got some awesome advantages here that we're looking to take care of. So thanks.
Thanks, Bob. Thanks, Sarah. Yeah, as Bob said, I actually the head of data science and engineering teams. So if you, I don't have a position right now, I just feel it, but other teams does, and also including the cloud teams, the media teams, and other teams. So if you're interested, just talk to me afterwards. Okay, so with that, let's introduce the first speaker. Wanda works for HortonWorks. He's the Apache committer and the PMC members. He has been working for Hadoop YARN for a long time. So I actually invited him to talk. I forgot it was a year ago when I worked at the last company. He went to a tech talk about the newest features in YARN. It's always a great talk. So today he's going to talk about TensorFlow in YARN. So I'm looking forward to that talk. Let's see.
Yeah. Hi. So I'm Wanda, and I'm from HortonWorks, and I'm Apache Hadoop PMC member. Currently, I'm leading the scheduler and the GPU development in YARN, and thanks GoPro for hosting this event. Yeah. So today my topic is to talk about how Hadoop ecosystem to boost the TensorFlow and machine learning technologies. This is the agenda today. So first, I will talk about the overview of the machine learning in real life, and I will talk about how YARN to boost machine learning workload, and we will talk about how how to do a click-through rate on a big data platform. The last is a short demo. So first is how a review of machine learning in real life. Yeah. So first, you may get a cluster with shiny hardwares, and you will have the storage. It could be HDFS, S3, or MySQL. So you store your data into the cluster and the storage. And then you may install the machine learning or the big data libraries like the Hadoop, Spark, or TensorFlow. And you need teams. First team is on the left side. It is a data scientist. So what they do is they will explore data and they will create a pipeline and they will find the best parameters. And once this is done, they will get the best demo they have been exploring so far. So they will save the demo, save the model to the cluster. And on the right side, it is software engineers. What they typically do is to load the model, and they will deploy the model in production. And once this is deployed, we can get an online storing or offline storing on the batch or streaming data. Yeah, so this is one paper from Google. It is called Hidden Technical Debt in Machine Learning Systems. So if you look at this picture, the machine learning core is the middle part, is the smallest part. Yeah, so it is a core of machine learning algorithms, which is a TensorFlow, for example. And besides that, there are lots of complexities. For example, how to do the computation, how to do the data collection, how to do the feature extraction, and how to do for example, the machine resource management. All these things are very complex, and we need all these stuff to make the machine learning can run well. Yeah, so I will briefly talk about the machine learning workflow. Yeah, so first is data pre-processing and feature engineering part. So everything comes from data. So on top of the basic the raw data, we will do the ETL, and we will do the feature section and feature encoding. And once this is done, we will get the features which we extract from the data. What we are going to do is to feed these features to the model training and model evaluation and model staging. So basically, we will train the model using machine learning algorithms by using the features. And the last part is the online service. So basically, once the model is generated, we can serve this as a service, or we can, based on this model, to do more experiments. So let's go to the first part, and let's zoom in. The first part is data pre-processing. So typically what we do is first we need to import the data from storage. It could be HDFS, AWS, or some DB. And we are going to operate on the data. For example, we can join the data, use Hive or Spark, and we can do the data exploration using Zeppelin or Jupyter, for example. We can show in the basic, for example, the basic histogram of the data, and we can do some sampling of the data to do some experiment, and we can do using for example Spark to split the data to the training set and the test set to do the training. And once the data pre-processing stage is done, we will go to the next phase. It is a feature engineering. Yeah. So for the feature engineering, the old way to do this is to do manually to design the feature, and but sometimes this doesn't work very well. So the deep learning can make the feature engineering to be simpler. For example, this is a machine learning training for the face detection. So on the most left side, it is from the raw data, and the deep learning algorithm for the first layer can extract some basic features, for example, the edges and the shadows, for example. And on the second stage, they can extract some more complex features, for example, the eyes, the nose, and some other important piece on the face. And on the last phase, it becomes the actual the human's face. Yeah, so I can talk a little bit about the model training. The model training is we have two different categories. First is some traditional machine learning models, for example, the logistic regression, the gradient boosting tree, and the SVM and LDA, for example. And we can use libraries like the Apache Spark, MLlib, and the XGBoost to do the trainings using the traditional machine learning approach. And on the other hand, there are some new deep learning models, for example, DNN, CNN, RNN, and LSTM. And we can use the latest libraries like the Tensorflow and MHNet or PyTorch to do the training. Yeah, so for the model training, the deep learning cannot fit all. So basically, we have lots of machine learning tests. For example, the natural language processing, computer vision, speech, video, anti-fraud, and recommendation. There are lots of tests. For the deep learning, sometimes it works well on some of the tests. For example, the deep learning works very well on the computer vision part, but for some other parts, it may not work very well. So in the practice, we still need to compare it with some traditional machine learning workload and see which one can get better result. Yeah, so the last part is the model serving. Basically, we will just take the model out and use its existing frameworks to serve the model. For example, we can use Spark to load the model trained from TensorFlow to do some batch scoring, or we can just launch the TensorFlow serving service on the cluster to do the online model serving. Yeah, so I just quickly go through the overview of the machine learning in the real life. The second part is how the Apache Hadoop YARN to boost machine learning workload. So I will first talk about what's the machine learning plus big data platform on YARN looks like. The first is we will get some hardwares on the bottom. We have maybe CPU, GPU, and SSDs on the cluster, and we have storage that's set up on top of the hardware, and we can install Hadoop YARN to manage the resource and also can load data from the storage, and we can deploy some batch job or the SQL frameworks like the Hive LLAD or the Spark SQL to do the SQL operations. And also we can deploy the machine learning libraries, for example, Spark, XGBoost, and TensorFlow to do the machine learning workload. And we can deploy Zeppelins to let the data scientists can easier digest and to explore their data. So here's the question: why we put all under YARN? This is a normal YARN user we see almost every day, and they want lots of things. The first thing is they want SLA. So basically, they want their job can be launched at some given time, and they want their job can be finished within some given time. And they want better monitoring. They want to see what's the stage of the job, and they want to see why my job gets stuck or why I cannot get more resources than some other user. And they want isolation, so they don't want the jobs from other user or the jobs from the same group to affect each other. So for the SLA, we have capacity planning. So basically, we can set up the queues, which can same as a hierarchy. For example, for the engineering department, they can have 50% of the cluster resource, and for the developer team, they may have 20% from the engineering group, and QA team maybe have 80% of the cluster resource. Once this is get planned, so they can submit jobs to different queues to get different resource. And we also have preemption. So if someone takes more resource than the guaranteed, we will the YARN scheduler will take in to kill some tasks to make the user can get enough resource. Also, we have a reservation system which you can reserve the resource before you submit the job, and also the latest feature has you can do the predictably to do the reservation. For example, you can reserve. I have a job which will run at 3 a.m. every day, and needs some resource. And for the monitoring, YARN recently added new timeline services which you can view and get all the history data from the storage. And YARN can integrate with the Grafana's, etc., to get better view of the resource. And for the isolation, we can do the isolations on the CPU memory, and also the GPU isolation is work in progress, and I can talk about this later. And some more are to be added. Currently, Intel is working on the FPGA isolation, and the network is also on the planning list. So YARN is the most popular production-ready platform to support both of online and offline service. So you may not be able to get this from, for example, Mesos or Kubernetes. You cannot get they to support the offline workload very well. Yeah, so this is an example about how we all running these stuffs on the same platform. So let's say we have 5-node cluster. Each of them has 128 gigabytes of memory, and they are managed by YARN. First, we can deploy. We can run in some test job, to run some high queries on the cluster. They will be allocated on some of the node and start running. And we can run Spark, which will run together with the test job. And we can deploy some long-running service, for example, the HyperL AP to do some interactive queries. And the department may get some more budget, so they added GPUs to the cluster, which we will also add these GPU machines to YARN to manage. And we can run TensorFlow by using this GPU machine. When the user wants to request TensorFlow to run the GPU machine, we will directly allocate the GPU resource for these tasks. And also they can run Caffe or the MSNet to consume the GPU resource and together with TensorFlow workload. Yeah, so I will briefly talk about the GPU support on YARN. First is why we need the GPUs, why we need to run the workload on GPU. Because GPU has many cores which can handle the massive but much simpler computation tasks simultaneously compared to CPU. So on the left side, it is a GPU. It has many cores, and on the right side, it's CPU. It has less but more powerful cores. Because for the deep learning workload, they are mostly the matrix computations. So these computations can be optimized when we're running this on the GPU. So we cannot see much benefit by putting this to GPU. So once we map this to the once we run the job, and the framework, for example, TensorFlow, will directly map the GPU computation intensive part to the GPU. And when it is get started, the GPU part becomes very can be done in a very short time. So the overall job performance can be improved. So without GPU support, the researchers or engineers are almost impossible to wait job to finish, because it will take several months to train some large model. It is impossible to wait for such a long time. The GPU support on YARN currently is on track, and the ETA is Hadoop. It will be released with Hadoop 3.1, and which is planned as January 2018. So this is a new UI added for the GPU support on YARN. So I'm working on this recently, so I just post some work in progress screenshot here. Yeah, the second part of new added to YARN, which can help the machine learning or some other general services, we call it YARN service assembly. We can make, by using this, we can make everything much easier. So I'm not sure how many of you have tried to write the YARN application master before. No? Yeah. So seems you are very lucky. So writing application master on YARN is super hard. So that's why we got several frameworks natively running on YARN. For example, the MapReduce, TED, Spark. So it is very hard if you want to implement something to run it on YARN by using the native application master API. It will take a lot of effort. What we do is we added the native service, which you can directly write in assembly spec in JSON. We call it YARN file. And by submitting this file, we can get the service running. This is very similar to the Marathon or Kubernetes. Yeah, and we will post the JSON as a REST request to the YARN server, and the YARN will figure out the rest of it. So here's an example. This is a TensorFlow training example by using the YARN assembly API. First, we will define the name of the job or service. Now the name is TensorFlow training, and it has one component called TensorFlow trainer, and there's no dependencies. So later I will talk about how we can use this to run some jobs in stages. And for this trainer, we have only one container here, and we will specify the artifact, which is a Docker image name, and we will specify the launch command. And also, we will specify the resource. In this example, we specified 16 CPUs and 32 GB of memory and 4 GPUs. So this one, the ETA is Hadoop 3.1 as well. So it is actually should be 2018 January. Yeah. So I will put several more examples about how YARN assembly to run multi-stage jobs. This is one job which has two stages. One is to run in the Spark preprocessor first, and it will run 5 container Spark job, and it will run the launch command to do the preprocessor to launch the job. And then we can specify the other component, which is a TensorFlow training component, and put the Spark preprocessor as a dependency. So once the first is finished, we will start the second one. And this one is an example about how to run the distributed TensorFlow training with parameter server. So we will have two components. The first component is a trainer. We will specify the trainer to use 10 containers, and this is a launch command. We will specify the command, and for some unsure parts, we can use the trainer 0 to 9 to note to represent the 10 trainers. And for the second component, it is a parameter server. We can launch the parameter server. Also, we can use YARN assembly to do some more stuff. For example, the parallel parameter tuning. So basically, we can write several trainers at one batch and submit these things all together to YARN. And all these trainers will get started when the cluster has enough resource, and we can monitor the training progress separately for these trainers. And also, we can use the YARN assembly to do model serving. And this example is to run the do serving script, and we can specify what's the model we want to serve. Here is using the Inception v3 model, and it poses a port, so we can connect to the port to get the model served. Also, when we specify the number of containers, the YARN can figure out how to do the load balancing in the backend. So when we count this is the host name. When we come to the serving.tensorflow model serving and some domain name, and the YARN will do the load balancing to choose one of the serving service to get the result. Yeah. Also, when we can imagine once we have the model file to be updated, we can replace the existing model file and just to do the upgrade of the images or the models. Yeah. So here's an example walkthrough about how to do the CTR on a big data platform. So here's a short introduction of the CTR prediction. So first we will, for the CTR, it is given a user and context. We will predict the probability of a click for an ad. And this is the most profitable machine learning programs. So lots of companies are investing in this. And there are some challenges. First is even if it's a simple binary problem, but what we want is not the predicted class. We want the probabilities about how much the user wants to click the ad or not. And typically, we have very skewed label distribution. So only a few users will click the ad. For the rest of the users, they just ignore this ad. So for the skewed label distribution, it's very hard for the machine learning to create some issues for the machine learning. And typically, we will have tons of data because we have so many users to generate the data. And we need to predict very quickly. We can't wait for 5 seconds to get the result. We want to get the result when the page is finished loading. Yeah, so this is an example of the data. For each entry, we have the impressions. The impressions, which is a context. We can think that, for example, the cookies is one kind of impression, and the result is clicked or not clicked, and they are all labeled events. we can use these events to do the model training. And here's the models typically we are using to do the CTR model. The most common are still the logistic regression to do the CTR to do the CTR learning. For example, the logistic regression on SGD and LBFGS. And also we have some newer models like the factorization machine and the GPT and the deep learning networks. So by using Zeppelin, we can make the Spark and some other libraries. For example, the TensorFlow can work together to do the CTR prediction. The Zeppelin can also be launched by YARN. We can running a container which hosting the Zeppelin server. We can log into the server to do whatever we need. So first is we can use the Spark to import data and do some data exploration. We can import the data from some HDFS folder, and we can count the clicks to get how much is how much times we get the user click on the data and how much time we get the user not click on the data. And we can do the sampling the data. We can only get some part of the data out and do the continue processing the data. And we can using the Spark to do the join and remove some NA values. And we can split the data to train and test set. Also, we can write the TensorFlow programs to directly on the Zeppelin to do the data and to train the model. And we can also write a trainer by using Spark MLlib and compare the result. Also, we can use a sharing functionality provided by the Zeppelin. We can share the notebook from one user to another, and they can continue explore the data. Yeah, so I can play a demo video which I recorded last time. It has 4 NVIDIA Tesla P100 GPUs. Yeah, let me start from beginning. Yeah, so here's a little bit background. What the demo taught is to using YARN to manage a cluster which has GPUs and CPUs, and we are running the 2 jobs on the cluster. One is using GPU, and another one is using CPU, and we compare the result. On this machine, it has 4 NVIDIA Tesla P100 GPUs. In addition to that, let's look at the CPU. It has 160 CPUs in this cluster. So what we're going to do next is to submit 2 jobs to the cluster. One will use GPU and CPU at the same time, and the other one only use CPU. We will compare the performance gain we can get from the GPUs. So this software is Postman. It's a better way to submit the REST request to YARN. And once we have the job select ready, we can use the REST API to post to YARN, so YARN knows how to launch it. So for the first one, we will look at its CPU job. We will give the name of the job, and it will have only one container in the job. And we will specify the Docker image and the version of this job. And this is the command we will launch to do the model training. And for this container, it will have 32 gigabyte of memories and 8 CPUs, but we will not allow any GPU usage for this job. So let's submit the job. Yeah, it is accepted. And let's look at the GPU job spec. So the only change is the name we change to GPU, and this one allows to use 4 GPUs. Okay, let's submit this as well. So let's go to the new UI to check these 2 jobs should be already get started. And the first one is for the CPU, and the second one is for the GPU. Both of them are in the run state. So let's check the logs. So on the left side, it is the output from the job which is using CPU only. And on the right side, it is a job which can use both of the CPU and GPU. So we can see that on the right side, it is already finished almost 200 iterations. And for each iteration, it takes only 0.4546 seconds for each step. And on the left side, it is just finished the first step, and for each step it takes 63 or so seconds. So it's almost 100 more times faster while this job is running on the GPU cluster. Yeah, so that's mostly my today's demo. Thank you.
So any questions?
So I know TensorFlow has, when you have GPUs available, CPUs, sometimes you can actually manually direct what data you're sending to what type of processor.
Mm-hmm.
How are you doing that with YARN? Is YARN making those decisions for you, or are you still able to?
Yeah. Yeah. So basically, what YARN do is when the user comes to YARN, it will ask how much CPU needed and how much GPU needed for every trainer process. And when YARN launches the process, it will make the process to be isolated. So that means when the process gets started, it only see the resource which are allocated to this process. Right? So when the TensorFlow process gets started, it will look at what's assigned to the TensorFlow process. For example, 2 GPUs plus some CPUs. It will map the operations on whatever are available to this TensorFlow process. Yeah, so basically you cannot use the resource which are already assigned to others. If we launch two TensorFlow process on the same GPU, we will likely see the out of memory issues.
So how do you compare to TensorFlow on Spark? I think the TensorFlow on Spark, the RDD, distributed data to different TensorFlow on different. How does it compare to that?
Yeah. So for the TensorFlow on Spark, it is the user experience is still very similar to Spark. The user actually it is a little bit weird to the end users. There are only few users are actually using the TensorFlow on Spark in their production, and the TensorFlow on YARN is most at the native experience. It will make no difference from running TensorFlow on the Mesos or running TensorFlow on the Kubernetes. You will get the similar experience. Yeah.
So you decided like one user take too much. What does it matter?
Yeah. So I'm not sure. So your question is about when YARN will kick in to do the preemption. Yeah. So basically, based on the allocated resource, for example, when For the YAR queue, you can set up capacity, which is the guaranteed resource to you, and also you can set up max capacity, which is the total amount of resource you can use, but we cannot guarantee it. So if we submit jobs to a queue which is already above its guaranteed resource, the YAR will look at the available resource in the cluster and give to you when at that time the resource is available. But if someone comes in to ask resource from some underutilized queues, the YAR will preempt the overused queues. So basically, it is based on the based on allocated resource. And there are some new changes in the YAR essentially available in 3.1 or later. So that one is it will look at the actual resource usage. So if someone comes in from an underutilized queue, and all the resources are booked but not fully utilized, this is actually the common case. So the user will ask for more resource, but in the real program, they didn't use all this resource. So YAR can leverage this part of resource to launch your process. And this can also avoid some unnecessary tail of the process. Yeah.
So does YARN
So basically, YAR is only manage the resource. So we can run the Spark applications on YAR, which the Spark can ask some resource from YAR and launch the process. So basically, YAR will not do anything regarding to the computation. YAR is just to serve in these computation platforms. You can run Spark, you can run TensorFlow, and you can run MapReduce. There's no difference in YAR's perspective. Yeah. Also, I forgot to mention one thing, which is the question from Chester. So you're asking the difference between TensorFlow on Spark and TensorFlow on YAR. The biggest difference is that TensorFlow on Spark doesn't support GPU.
Graphically, on the paper suggested if you use YARN, then you could make optimal use of the GPU. Mm-hmm. Are you saying that you get some speed up running TensorFlow on the YARN?
So actually, it is get speed up by using the GPU. So what YAR provides is it can more smartly to manage these GPUs. It will give you better GPU isolation and give you better GPU management. Also, you can put the resource before you arrive to get the GPU resource.
The integration, when you start the TensorFlow workflow, does it reserve the whole resource from the very beginning all the way until the TensorFlow flow finishes, or it split the task into smaller chunks? And especially for the GPU side, when it actually uses it dynamically allocate those resources and frees it up.
So this is a very good question. So for the GPU usage, currently it is the time we allocate GPU is same as the time the process is running. This is because the TensorFlow itself cannot. So unless the TensorFlow can give up GPU use, we cannot take the GPU to other applications, right? If we take the same piece of GPU to the other application, but TensorFlow says, I want this GPU, the out of memory can happen.
Work runs for example, a week, then during that time, this cluster, that part of the resource is going to be.
Yeah, that is true. And also, because the TensorFlow is so intensively to use the GPU, it is actually it's very hard to give up GPU usage in the middle time.
So I think what I'm still not getting is, so if I have a cluster of CPUs and GPUs, and I have TensorFlow written, and
in TensorFlow, I specify I want this, these computations going to CPU, these computations going to GPU. I can do that today at TensorFlow, and I don't need YARN to do that, right? So what is YARN binding? So that's what I'm trying to make.
Yeah. So basically, what YARN gives you is to make the different applications can coexist in the cluster, right? So otherwise, if you yes. So for example, if you only have one GPU host, it is very easy to manage, and you can manage manually to launch the jobs. But if you have 100 GPU machines, actually we see some customers in that case 100 GPU machines, and every machine has 8 GPUs. In that case, we have to use some framework to manage this GPU instead of manually do that.
And to ask the obvious question, how does this compare to Kubernetes?
Yeah.
That's the question. Using Kubernetes for
this is a challenging question. So for the Kubernetes, the pros of Kubernetes is it has better support of the Docker container, and currently we are trying to fill the gap. But for the Docker container user experience, if you are so intensively use Docker container, maybe Kubernetes is a better operation, a better option. And for YARN, it is mostly very good for the running the offline workload and the online workload on the same cluster. So because it has many echoes, securities, and it can also can dealing with very fast job allocation. For example, if you want to run a MapReduce job with 1 million of tasks, YARN can give you all the containers in less than 1 minute. But for the Kubernetes, it will take a long time to get launched. So in the largest YARN cluster in the world is in Microsoft. They have a 40K nodes cluster. But the largest Kubernetes cluster, if I remember correctly, it is only a few thousands. And because it is running the long-running service, the number of allocations for every second actually is very low, because for the service it gets launched, and typically you don't want to shut it down. But for YARN, you are consistent and that's a job to be launched and stopped.
Often in the GPU computation world, you need to pin the memory on the GPU, which means you have a startup cost associated with the job. You actually want to launch a service and keep it on that GPU system.
Yeah. So for the YARN, the currently isolation GPU is no difference from how the Kubernetes do the GPU isolation. Basically, before start the process, they will pin the process to one or more GPU process, and they will these GPUs can be exclusively used by the process. Yeah.
There's no CPU using in the second or GPU.
No. So basically for the two jobs, they're both using CPU, but the second job using CPU plus GPU. So basically for the TensorFlow, even if it is very intensively used GPU, but it still must to have some GPU to have some CPU resource to run the other operations other than GPU part.
So just coming up to that question about you talked about multi-phases jobs for YARN. For the current version, like how many parallel operations can do for a job, either with any side of the cluster, and if there's a limit, then
So your question is how many stages we can specify? Actually, we haven't tested that, but yeah. So typically, I think for the most use cases is several stages, because this spec is specified manually, right? But if we want to support some dynamic specify some stages, we haven't think about that yet. Yeah.
Okay, great. Thank you. Thank you very much.
Thank you for joining.
Well, we have a second lightning talk. This is going to be a quick introductions from IBM. It's Mike and Madison from the IBM Spark Technology Center. So they're going to give you a little introduction to what they're working on, and I think either next month or the month after, I don't know. I haven't talked to him about the schedule yet, but it's quickly going to do a full talk for the research work they have done.
Thank you. Thanks so much, and that was a great talk. Thanks for that as well. All right, so this is Mike, and I'm Madison, and as we were introduced, we're from IBM Spark Technology Center. Awesome. Thank you. And we'll be talking about mitosis detection today, so it's pretty exciting. So a little bit about the Spark Technology Center. We were founded a few years ago. We're located downtown San Francisco, next to the San Francisco MoMA. Great location. Stop by. So our main mission is basically to contribute intellectual and technical capital to the Apache Spark community. But beyond that, we're really focused on cognitive technology and cognitive open tech. So we're all about open source, really cool projects, such as detecting breast cancer. So we have a bunch of different projects going on like this that are interesting, but we'd love to move forward with this while we're here today. So we're really interested in coming up with a really interesting project around last year. We're both really interested in health. Mike used to go to medical school, and I used to work in health policy. So we're very passionate about this, and Mike came across this contest where he discovered the data set has now been worked.
Thanks, Madison. All right, so with that intro in place, let's get into the actual problem. So like we said, we're working on a problem for mitosis detection in deep learning. And so here we have an image of a piece of breast tumor tissue that's been sliced up, stained with an agent to show off different cellular structures, and then placed under a microscope to be examined by a physician. And so the goal in this case for a physician, when they get this kind of piece of tumor tissue, is to be able to classify the severity of this tumor. Because a tumor in a patient can be either relatively benign, and that may be a good prognosis, or it can be relatively malignant, and they may need like further treatments or other further aspects. And so it's a difficult process and very important one. And so for breast tumors, usually the first subtask that a physician in this case will work on is to identify and locate all of the cell mitoses in a region of the tumor. So this image kind of represents a region of the tumor that a physician might see when they look under a microscope. They'll see like smaller portions and scan around for that region. And so they'll look through this, and if you look at this little tiny blob that we're pointing to, and it's enlarged on the left, that is a cell mitosis. And so without getting too much into the details, like medical details for it, when cells undergo mitosis, that's the process of cells dividing. And so in other words, it's the way that tissues grow. And so when they do that, the DNA inside the nucleus, it unravels. Otherwise, it's very faint and very tightly wound, so you don't see it as well. Unravels, it takes up most of the nucleus. They peel it apart so it can be replicated, and the cells will pull apart a pair of the DNA. And so when it does that, our stain that we have on the tissue will stain these nucleic acids a dark blue. And when you see this mitosis right here, instead of just being a round circle that mostly is pink, a little bit of blue, we see a very big blue blob. And to a trained physician, they'll say, oh, that's a cell in mitosis. And if you look in the center, it's actually a particularly interesting case. You can see a cleft in the center where the cells are starting to pull apart. So it turns out there's actually a few other mitoses here as well. And they have different characteristics depending on when this tumor tissue was biopsied, as well as like the three-dimensional aspect, the way this was sliced. So it's a difficult process. And despite extensive training that a physician in this case will receive, it ends up being prone to issues of subjectivity. And so the challenge here is to develop an algorithm that, given this image of the tissue, could automatically detect those cell mitoses and thus kind of aid the physician in their ability to treat. And so we're treating this problem as an image object detection problem, and we're working on a deep learning approach involving convolutional neural nets. So this is kind of a general outline of our approach. So imagine we have these raw images of the tumor tissue with locations of the cell mitoses. And based on the fact that we have relatively few images and the mitoses of interest are relatively small on the image rather than a large region like a cat or dog image, we're electing to generate versions of the data set where we cut up the images into tiles. And then we make use of pre-trained convolutional neural nets, BGTs, ResNets, whatever. We modify them slightly. We'll fine-tune various regions of those models. During training, we'll make use of data augmentation, kind of just standard practices. We actually make use of trained models to go back and bootstrap the generation of data sets that are more difficult to train on. And then we'll also make predictions for the actual coordinates of what we believe to be the mitosis locations. So a lot of interesting aspects. We're going to save the details for that future talk, so this will just serve as a teaser, and we'll go deep dive into the algorithms, the math, and all that aspect of it next time. And so for the next few minutes, I actually just wanted to, since we don't want to get into pieces of that, it'll take a long time, I just wanted to pull out one aspect to kind of like leave as a nice takeaway that I found to be useful for working on machine learning problems, and that's having a good experimentation workflow. So kind of the way I see it, machine learning is science, in the sense that we come up with ideas or questions that we aim to explore. Right? So in our case, it's mitosis detection. And then we create hypotheses, right? These are what type of model, what kind of general approach do we want to take? Do we want to use regularization or what particular architecture, et cetera? And we design experiments that we actually want to run so we can test these hypotheses, right? So these are the actual code that we're training our models with. And so we run these experiments, we evaluate them singularly, and then we compare them with each other, right? Both in the current as well as past experiments. And this process continues in a loop where you're constantly refining hypotheses, you're designing new ones, you're designing new experiments, running them, comparing results. And ultimately, this continues until you reach, you achieve kind of an end goal that gives you a satisfying answer or conclusion to the original problem or idea that you set out to explore. And so overall, I found that just in general, having a good workflow to support this type of experimentation is extremely useful for trying to achieve success on a machine learning project. And so with that in mind, I just thought I would real quickly kind of go through just kind of the components that I found useful. And the kind of key takeaway here would be, yeah, the specifics might be interesting, but maybe just next time if you're approaching a machine learning problem, maybe think about having a workflow so that you can focus more time on the problem itself and the math. And if you're building tools or services to support machine learning, maybe think about, can this help improve someone's workflow, or does it fit in nicely to conventional workflows? So for me, and I think all of these aspects, I mean, not the specifics towards me, but the aspects may be more broader. Up in the left, just so we have some context, this left-hand side of the terminal, this is a TensorBoard window on the right. On the left-hand side of the terminal, there's a local file. Upper right is a local terminal. Middle right is a terminal on a remote server. And bottom right is a local file. And so kind of the number, I have 6 pieces to my workflow. And the first piece is an experiment journal. And so I think this is probably one of the most important pieces to me. And so that's kind of the local file, this bottom right. And this is the journal where I keep track of everything. So I keep track of hypotheses, right? What am I trying to experiment with? I keep track of the experiments themselves. How did I run the experiments? Where are the experiments running? Which machine are they running on? How did I start running this experiment? Importantly, what are the goals for this experiment? Like, why am I running, right? That's a part of the hypothesis. And when you have experiments that take multiple days and you're running multiple in parallel, it's useful to be able to remember, why did you start this experiment? And then I'll also have results as well. Right? So once these experiments are complete, not necessarily track every single numeric aspect of it, because there's other ways to track that, but I will keep track of just at least a written description of the results. What did it achieve? Did it achieve or make any progress towards the goals I had for that? Did it uphold the hypotheses or not? And I maintain all that in a file so that I can quickly see what I've been working on, what's currently being worked on, what's worked on in the past, and I can go back and compare or restart experiments that are slight modifications of previous ones. So I use a markdown file for that. I think there's possibilities to expand that more into a service, or maybe even embed it, say, in TensorFlow or TensorBoard, rather. But just that meta idea of having a journal that you keep track of things is useful. So then, like, once I say I have an experiment designed, right, I have some hypothesis I want to test, and I've designed some experiments, I'll actually go write the code for that, right? You need to have the code so you can run. And so I tend to do development locally on a machine. And so I'll write on any code I need to be able to run that experiment. I'll test it locally, maybe write unit tests, or just run it, make sure it has the behavior that I'm hoping it will have, maybe debug it, make sure it's outputting the appropriate logs that I'm hoping it will have. Any running I do locally will be more proof of concept because these are very expensive models, or I might use a like a dummy model just to make sure the rest of the algorithm's working. And so once I have that kind of done, so I'll be writing stuff and running stuff up here. I'll have a set of GPU servers. So it's interesting going after the previous talk because it opens up some interesting possibilities. But I just have a set of raw GPU servers that I manage myself. And so I will push the code for whatever experiment I want onto the servers. I'll make a note of which server I'm using at that moment. So once again, it's kind of keeping track of what I have. Having a system that maybe manages that for you could be very useful. Nonetheless, I'll throw it up there. And so once it's on there, I found it's very useful to have some system in place that will let you run the experiments and keep them running in the background so that you can detach from them, walk away, come back at some other point in time, reattach and monitor, or even kill the experiment depending on the progress of it. So currently what I use on raw servers is tmux, just to have ability to create sessions, attach to them, detach as needed, and reattach at a later point. But you could imagine have a different service that did this for you and managed it for you. And then during experimentation, I do make heavy use of logging. So, logging out basic things like statistics that I'm interested in. So F1 scores or loss values or different metrics that I'm interested in actually optimizing. And so that's kind of what you can see on the right here. Talk about that in just a moment. And also we'll put model checkpoints. I'll actually put out the code that I use to run this experiment, basically everything I need to be able to evaluate that experiment and rerun it if I need to. And so I found that given all that stuff you've logged, it's very useful to have a process in place that will let you explore that running experiment in real time, as well as compare it to past experiments. So for this project, I've been using TensorBoard. The project itself uses TensorFlow, so it's natural to use TensorBoard. Luckily, you can use TensorBoard from other projects as well. But I found it incredibly useful because you can monitor experiments in real time, which could let you go kill experiments if you no longer decide you need them. But also lets you compare them with previous experiments, and you can select whichever ones you'd like to compare with at that moment. And so that's what you can kind of see here. So you see F1 graphs here with, and I'm writing training and validation evaluations for that metric. Just in general, though, having that ability to do that in real time is useful. So that's kind of generally the workflow that I have, just a way to keep track of experiments, develop the code you need to run them, have a system in place that you can throw them onto a server to run, and have a way to evaluate and see them in real time and compare. So I just thought that would be a nice takeaway. So once again, if you're thinking about working on machine learning, maybe just think about a workflow so that you can focus more on the problem and the algorithms. If you're working on tools or services, maybe think about how you could enable someone to have an easier workflow so they can focus more on the problems. And so with that.
All right, so I want to thank you. Again, we do a lot of open source projects that focus on machine learning and data science. The SDC is full of data scientists like us, and they're all available online. So if you want to go see some completed projects, you can go to these links, and Mike's will be completed soon. He'll be posting journeys as well with all of the details. So thank you, guys.
Any questions for them?
So
yes.
Is the ultimate intent to score more slides?
For the actual project? So like I said, like in medical practice, one of the issues they have is subjectivity. And so, two highly trained physicians may not agree on a single slide. So luckily this data set we have about, I think, 50 physicians that made a joint agreement on them. So it's more objective, trying to pull out some of that subjectivity. So you hope is that with having an automated system, you would remove that subjectivity and have a more objective measure so you could aid the physician. So not necessarily trying to replace them by any means, but you can imagine being able to run this across a whole tumor and pull out candidate regions that the physician could use. That's the one piece. The other is that I showed one region, but if I had other slides, reality is that you have a much larger area of tissue. In real life, it's very small, but once you zoom in, it's much larger. And so typically what happens for a physician is they look at that very zoomed out and they'll pick which region they think is the worst because they don't have time to look at the whole thing. And so then they get one region. But if you had a model doing it, you could actually run it across the entire piece of tissue and get a much better reading. So you aim to try to improve the accuracy and aid the physician. Yeah, no, we could do it densely completely. Yeah. So us two are working on it. I'd also like to shout out Fei Hu here as one of our interns who's helping work on the inference part. So once you have this model trained, that's one of the other parts is how do you run it densely across this huge thing. So he's working on using Spark on a GPU cluster to actually make inference. So there's about 3 or 4 of us working on this project.
How much is database?
How big is the data? So there's 2 data sets. The main data set, because the ultimate what we want to work on is the actually classifying the severity. This is the first task towards that. For that, there's 500 gigs of highly compressed data. Once you uncompress it, it would be more around 7 terabytes. This data set, there's an auxiliary data set specifically for the mitosis part. It's much smaller because it's much smaller images. I don't have the exact count, but much lower. Excuse me? How do you compare them? So what do you mean by compare? I see, okay. So in this case, that's what's great about it. You can, for this subtask, it's a binary classification. So it's either, is this region, this image proposal region you're looking at, is it of a cell mitosis? So is it a cell that's dividing, or is it not? So we actually won't necessarily grade the mitoses themselves, but the kind of the next step when you wanted to grade the overall tissue in terms of severity, a physician will make use of the counts based on the density of mitoses in a region. And then there's some medical practices that says if the density is this high, then that could lead to this level of severity for this tumor tissue. And then there's a couple other measures. This is one of the biggest ones, but there are 2 other measures that will also take in place, namely about how or how regular all the cells are together and how basically if they're forming larger structures, more medical tasks. But that's how they would use it. So count the mitoses and then kind of make an estimate based on the density. Not with this data set. Yes. Yeah. So this is an image problem, right? And so a convolutional neural net, that like kind of design structure is ideal for image or data sets where you have spatial orientation. So an image has a 2-dimensional spatial aspect to it. And so that's ideal for a convolutional neural net. And one of the things too is that you're going to have a convolutional neural net that has some input size. We're choosing 64 by 64 because it's roughly about the size you would need to have a cell contained in it. And so if you run it across the entire image, it doesn't matter where in the image the mitosis is, so long as it detects it within a 64 by 64 region. And so convolutional neural net is good for that. And then going towards the noise part of it too, that's in how we sample for tiles. So I was saying, kind of get to that part, we have these big regions of the tissue, and you're right, there are only a couple mitoses, and most of it's not mitoses. It could be other cells, it could just be intercellular material in between different cells. But we know where the mitoses are based on the labeled data set, so we can sample those patches out as tiles, and then we just sample from the rest of the whole image to build up a training set of either a mitosis image or not a mitosis image. And so that is one of the problems, and that's why we use this like model bootstrapping technique, where we'll go back, we'll pull a data set, and imagine like if you have a cell mitosis, that's a dark blue image region, right? The hardest ones will be a normal cell that has a big nucleus. It's not undergoing mitosis, but it still has a nucleus, so it still has a dark blue region, just not as big. Whereas if you grabbed a patch with just pink regions, which is just in between the cells, that's not a very difficult patch. And so we'll go back with the trained model, go back into the data set, and we'll recreate a new data set where if the model misses it, like an initially trained model, if it misses one of the patches, then we'll say that's a very difficult patch, and we'll oversample that one and undersample the other ones that are easier. And that helps us combat the noise issue. Go ahead.
Does your work on African American and Asians too?
Yeah. So this is at the very low cellular level. So that tends to not have as much diversity in that sense. Totally, yeah. And probably the bigger thing too would be, this is specific to breast tumor tissue. Other types of tissues in the bodies will have different aspects. And in some tissues may even have more mitoses in this tumor area that may be fine for that type of tissue. But this is very specific at this point to this tissue. Although I think you could use this, if you train this model, you could use this as a pre-trained model and apply it to a different type of tissue. Should be an interesting area to look at. Yes.
I think like given the nature of data that you already have, it is like input is a 2D image, and I use like how many those spots are there. But the actual problem that it will solve is like you get the 3D like image of the breast cells as an input, and you want to count those spots in 3D.
So this is a different data set. So I think you're thinking more mammograms. So that's a three-dimensional. It's more a black and gray scale type of image, and that's looking at it in a 3D sense. This would be if you do a biopsy on the piece of tissue. I may not have mentioned that, but you biopsy that piece of tissue out, and you slice it up very thinly, and you're laying a thin slice onto a slide and putting it under a microscope. So it's mainly two-dimensional in that sense. So that image is a pretty good representation. However, there is a bit of a 3D sense because no matter what, if you slice it, even very thin, with a microscope, you can change the exact zoom level. And you can just slightly change it from a cell that's at the very top of the slice towards a cell that's just slightly below it, even though you wouldn't be able to tell that by the human eye. So there's a slight thing there, and you miss that by taking just a single two-dimensional aspect. But that's just very small. It's much different than if you have a big 3D volume for a different type of scan.
Given at this point.
Yeah, and
recognizing these in 2D image as a sample.
No, this would be still somewhat close because this is a task that physician does, and then we'll use it. But yeah, if you want to get more into exactly, there's a little bit of tricks you can do with the tools, but mainly it's 2 dimensions. But it's a good thing to think about too. If you had that 3-dimensional, if you could just slightly change the zoom on, it would be interesting to look at.
Reduce how much effort and time a physician has to put in.
Yeah.
Right. But maybe in the far future we can do something serious.
To your point, it's actually a series of slides. There are relationships between these slides. Yeah. You know, what you're saying.
Yeah.
Yeah, at the extreme, you could have the entire chunk slide, the order of the slide, and yeah, relationships.
Yeah.
I think that will be the last question. So thank you very much.
Cool.
We have another meetup talk next week at the Lift. So it's going to talk about the Apache, Flink streaming and HBase from Salesforce, and also the data Lift. They basically talk about their data platforms. So it should be very interesting talk. So that's next Wednesday. It's in the Lift in San Francisco. And we are planning for other talks, and we haven't finalized the Google Brain and said they're going to give a talk at the end of the next month on their neural network sequence-to-sequence type of talks. But I haven't got the abstract yet. But if nothing changed, I should have got it within a week or two. So that'll be next month. And of course, I'll work with Mike and Matt and try to find out what's the best schedule for that talk. So, well, welcome all of you. And next time when we schedule in GoPro, be sure to come because it's going to be a kind of free GoPro camera. Okay, thank you very much.